All right, everyone. So today I'm going to start by taking length theorem, which we proved last time, and generalizing it to higher dimensions. So for the most part, the proof that we gave last time works for higher dimensions. Is just something sort of interesting to consider about the correct generalization of the statement. So instead of c star squared, we're going to consider c star to the n, which again is an algebraic variety. We can multiply the point inside here, so this is still an algebraic group. And let's say some number bigger than or equal to 1. And so before we sort of had to separate it out in this somewhat artificial way, sort of torsion points in here, which are points where the coordinates roots of unity, c star squared, and this sort of one-dimensional guy. Of course, now we have c star to the n, so there's a whole sort of range of things in between. And things sort of change a little bit, it becomes a bit less natural. So instead, we're going to consider a subvariety G as an algebraic sort of a definition. G is an algebraic subvariety. Closure multiplication. So I want G to be a subgroup, but also an algebraic. In C star to the torsion coset. As an example, G is the set of x, y, z, satisfying like x to 5, y cubed times z is equal to 1. This is an algebraic subgroup. This one I think has and you could take sort of to be the torsion point, let's say 1. Multiply them by this coordinate, so you flip z. So now all algebraic sub in the concrete. Start. So it's easy to see. Right? And such feed. And help which exponent to sort of throw it. So, and
Cutting out or something, I don't know why.
in case we're going to show this, it's clearly necessary. And once you have this claim, you can sort of go by induction. I don't sort of want to go through that, but once you have this claim, it's not hard to finish. Okay, so we're going to prove this claim. And so we'll go by induction. So, you know, n equals 1 is like really easy. If you have some finite subgroup of C star, bunch of reducibility, they're all of some order, some power of them is trivial. So let's assume that it's true for n, and do the case of n plus 1. Okay, so consider the projection from C star to the n plus 1 maps to C star to the n. So we'll just ignore the last coordinate, or whichever coordinate you pick. And we're going to restrict this projection to G. And then we have a bunch of cases. So case 1, pi of G is not all of C star to the n. Okay. So in this case, pi of G is an algebraic subgroup. This case is sort of easy because then we have a character C star to the n. We can just use the same guy over here, ignoring the last coordinate. Second case is pi of G is all of C star to the n. Now G is n-dimensional and C star to the n is n-dimensional. So this map has a zero-dimensional kernel. And the kernel is also an algebraic variety, because we're in the world of algebraic varieties. So this means that the kernel of pi is finite. Of some finite order, let's say m. For some positive integer m. Now, if we replace G by the group G to the m, so instead of replacing it by all mth powers in G, we can assume, in fact, that the kernel of pi is restricted to G is trivial. Okay? Now G to the m is also an algebraic subgroup, and if a character vanishes here, then the mth power of the character vanishes here, so we can make this reduction without changing the claim. Okay, so we can assume this kernel of pi is actually trivial. So, since the kernel of pi is trivial, therefore this map from G to C star to the n is an isomorphism so G, so we can write sort of, if we let F be the inverse of phi, we can write f of x1 through xn. Well, we know that the first coordinates have to remain the same.
You mean pi? Inverse of pi?
Sorry, inverse of pi. There's my phi. Thank you. Then f is this, together with some polynomial g, or Laurent monomial g. So the first n coordinates have to remain the same. And because g is a subgroup, we know that g of x1 times x2 has to equal g of x1 times g of x2. And from this, you need to check that g has to be a monomial. So g is a monomial. Okay. So once you have this, you can just take chi of x1 through xn plus 1 to be sort of x1, x2, x3, xn times g. You can take chi to be xn plus 1 times g inverse of x1 through xn. And then this gives you a character which is trivial on the group G. Okay, and that's the end. Any questions about this? So we're sort of cheating a little bit, right? Like ever so slightly. We're just cheating in this step here. So it is true you have sort of some function g which gives you the inverse, and I sort of concluded that g is the wrong polynomial simply because we're sort of in the algebraic world. Okay, so this is actually, it's true, but some more words have to be said, which I don't really want to say. Right? But you can in fact do this. Okay? And there's sort of other proofs you can give. In this world, but this sort of basic game is one we'll be playing a lot. So we're sort of go by induction, we'll stratify by dimension, we'll use the fact that we're sort of in some nice category throughout the way. Here we sort of mainly use algebraicity to give us finiteness, which is also something we'll be using a lot. Any questions about this? All right. Okay, so now we sort of understand what the algebraic subgroups look like, and therefore what the torsion cosets look like. And so now you sort of, we want to generalize the n equals 2 statement. And so what should the generalization be? Well, so one statement we can make is the following. So we could say, suppose v is in C star to the n, and suppose it contains, suppose v in C star to the n, and suppose v contains no positive dimensional torsion cosets. Okay? Then we could hope it's like try one. You could hope that V intersects C star to the n, so it takes function many torsion points in general, right? That's one generalization of Lang's theorem. That if you contain infinitely many torsion points, you have to contain at least one positive dimensional torsion coset. And in the n equals 2 case, this is actually equivalent to the statement we proved. Okay, but this statement is true, and we'll prove a version of this, or something more general than this. But in fact, it's not really the strongest statement you could hope for. It sort of leaves much to be desired. The reason is that you can sort of ask, well, what happens if you do contain a torsion coset? And sort of the natural guess to make is, well, then you can reduce it to a case like this for lower dimension. That's not quite true. There's sort of two parts to this conjecture. Sort of the point is that torsion cosets come in sort of countable unions of algebraic families. This is all very heuristic. But it's sort of good to keep in mind the structure of what's going on. So what do I mean by this? So one sort of family that torsion cosets come in is you can fix your sort of L that we talked about, sort of the shape of your torsion coset, and vary the root of unity you're translating by. Okay, so one sort of the algebraic family or an example of an algebraic family, quote, because I don't want to make this precise, is sort of fix finitely many characters inside what I call G dual, inside what I call the, call it in POM C star to the n to C star, and finitely many roots of unity. And now insist that chi I of t is equal to zeta I. So this is a torsion coset, if you insist this for all I. And then what you can do to make it an algebraic family is you can vary the roots of unity that you're picking. Okay? So this gives you sort of a family, an infinite family of torsion cosets. One example of this is the torsion points, right? You could fix sort of a basis, n characters here, specify what each basis vector character evaluates to, and then just literally tells you which point you are. So sort of one case of this is sort of the algebraic family of just torsion points in C star to Vn. But there's other cases. For example, you could look at the family where x times y is some root of unity, keep varying this root of unity, and that gives you like infinitely many torsion cosets, all of which sort of have the same shape. They're all translates of each other. Okay? And if we just sort of are interested in these torsion cosets, we sort of fix a particular algebraic family and ask like how many of them does V contain or something, that reduces to this statement pretty quickly. Okay? For that statement, you sort of just look at the map chi1 through chi-m on V, you look at its image, you ask where that sort of has full fiber. That's an algebraic condition. It's not clear, but you can work a bit to make it an algebraic condition, and then you've reduced the zero-dimensional case. So this is like one example where this statement is essentially enough to understand this family of torsion cosets. But there's another example, another type of family. So this is sort of the non-algebraic family. And this is essentially where you vary the characters chi. Okay, so sort of the easiest example to keep in mind, or one sort of easy example to keep in mind, is if you take n equals 3 and say, look at the family where x to the k times y times z is equal to 1. K is some positive integer. Okay, so this is some infinite family of algebraic subgroups inside C star cubed. And now I can say, given an algebraic surface, is it true that unless I'm some algebraic subgroup, I contain only finitely many of these? It's a very natural question to ask. And for this kind of question, because sort of the character of these varieties keeps changing, you can't really reduce it to a statement like this, as far as I know. Okay? My only point sort of is that it's really not enough to look at this zero-dimensional case. The general case is a little bit more complicated, because you have this additional variation of the shape of your variety. All right, so here's the actual generalization, or, well, in my mind, the correct generalization. This one is also true. But it's going to be subsumed by what we're about to write down. Let me make sure I get this right. So, this was first proved by Raynaud. Was subsequently proved by many, many more people. So it's the following. Suppose you have V in C star to Vn, some algebraic variety. then if you look at all the torsion points inside V, there might be finitely many, there might not be finitely many, but these guys are contained to the union of sort of finitely many varieties Sj, which are torsion cosets which lie inside V. Sj is a torsion coset which lies inside V. Okay? So what is it saying? It's saying that your variety V, it contains finitely many torsion cosets, such that every torsion point is inside one of these cosets. Okay? And there's sort of clearly nothing stronger you can say, right? Because you can imagine like taking finitely many of these torsion cosets and just coming up with some random variety which contains them all. And you have no control over what else you put into the variety, but it's saying that if you want to throw in more torsion points, you have to throw in some more torsion cosets as well. So in particular, this is implying this case, right? Because it's implying that if you have infinitely many of these, then one of these has to be finite dimensional. It can't all be zero dimensional, because you have to account for infinitely many points. Okay? And it is a stronger statement, right? That it, for example, handles the case of this. If you have an algebraic surface containing infinitely many of these, well, these guys each come with their own set of torsion points, but you only have finitely many guys you're allowed. Yes?
In the family up there, are you saying that that this holds for all k? I mean, how is it a family? What's moving? K?
Yes, k is moving.
So if you can, and this is points x, y, z that satisfy this for every k. Doesn't that mean that x is 1?
No, sorry, I don't mean that.
You just mean like a union of all points.
Yeah, I just mean the union of all these
For
guys.
some k, this holds.
Exactly. Yeah, I'm saying look at all the points are for some k. So I think of it as you have this infinitely many algebraic varieties, and for some k this holds. And then I'm asking sort of how many of these guys can be contained inside some v. And I'm just saying that's not addressed by this kind of statement, but it is addressed by this kind of statement. Other questions? There's another way to state this, an equivalent way. So equivalently, sort of a slicker way to say it, so it's easy to get confused with it, but a slicker way to say it is that V contains finitely many maximal torsion cosets. Okay? By which I mean torsion cosets in V, which are contained higher dimensional torsion cosets in V. And then all the torsion points sort of have to lie inside one of these Tor equivalents. All right, so the hardest thing about the statement is making it at this point. Once you made it, the proof isn't actually all that different what we did for the n equals 2 case. So let's go through it sort of a little faster than before, but we'll still cover all the steps. So the first step, once again, is we reduce to Q bar. Okay, it's a very common step in the arguments, and it might seem trivial now, but later on I'll give you some cases where it's not trivial. Like we still don't know how to do that. So it's something to pay attention to. But the way to do it here is you replace V by W, the intersection over all sigma in the Galois group of C over Q bar of sigma V. Okay, so we made this argument before in sort of slightly less high-powered language. This is the more high-powered way to say it. So if you have any torsion points inside V, they'll certainly be inside sigma of V, to all sigmas, because these sigmas leave your torsion points alone. They're all inside Q bar. And what I mean by sigma of V, well, just like before, I mean take like a bunch of polynomials that cut out V and apply sigma to all of them. That'll give you sigma of V. To contain exactly the points, which are sigma of the points in V. So the only thing to check is that this is still an algebraic variety. Be a little careful because this is a very, very infinite intersection. And so this is some sort of basic algebra. So this is an algebraic variety. Basic doesn't mean easy though. Because sort of the ring of functions on C star to the n, Cx1, x1 inverse, xn, xn inverse, is Noetherian. Right, so you can write this as some descending chain of varieties, keep intersecting more and more guys, that corresponds to some increasing chain of ideals. Chain of ideals must stabilize, therefore the intersection must stabilize as well. We're allowed to intersect infinitely many varieties and still get an algebraic variety. Okay? You can make the argument in more concrete terms as well, where you keep track of like the number of components of each dimension, and then each component of a dimension becomes smaller, it has to become components of lower dimensions. There can be finitely many of those. So you can set up some sort of complicated reduction to try and make that work, but sort of this is a very clean way to think of it. Noetherianity is sort of the source of a lot of these stabilization theorems. All right? Okay, so once we know W is a variety, then sort of W is defined over Q bar. So we can just deal with W instead of V. So from now on, we'll assume V is defined over Q bar. This is really a Q bar kind of statement. Okay, so the second step, like before, is reduce to V defined over Q. Like before, it's not strictly necessary, but it will make the equidistribution step a lot simpler. And again, we just do this by instead of V, we deal with W, which is a union over all tau inside, well, the Galois group of Q bar over Q, if you like, of tau. So V is defined over Q bar, so it's defined over some finite number field. This is really a finite union. We're allowed to take finite union of varieties and stay in the world of varieties. Okay? And this is just like before, where V is defined by polynomial. What this is doing is just saying multiply the polynomial by all of its conjugates. Okay, so far we've done basically nothing. Okay, so now we're going to suppose, without loss of generality, for a reason that I'll explain, that for any finite set, chi1 through chi_m, of non-trivial characters, and zeta 1 through zeta m of roots of unity, that it is not true that it's not true that people can still see here, right? Is there anything left? Or maybe I'll go out here just in case. It's not true that if you look at all the torsion points in V, that they satisfy one of the relations, chi I of that point is zeta I. They're inside the union j equals 1 to m of the set chi I of t equals zeta I, zeta j. Okay? So what we're saying that we're going to assume that it's not true that for any finite set of proper torsion cosets, all the roots of unity inside V are contained inside one of these torsion cosets. Okay?
And it's not fixed or anything, right?
N for our statement?
N? Like
Sorry.
N?
No, M is not fixed.
That's
For any finite set. Yeah, that's very important. Okay, so why can we assume this without loss generality? Well, because if this were true, if we could find some finite set of proper torsion cosets with this property here, then we could replace V. So if not, we can replace V by the union of V intersect chi j equals zeta j. And each one of these lives in a lower dimensional algebraic group. So in C star to the n minus 1 instead of C star to the n. And so this reduces n to n minus 1. Right? Why should we go this step?
I guess it's easy to show that that's a torsion coset.
That's what? I'm sorry?
That the B intersect chi j equals zeta j, that those are torsion cosets or something. So that's like easy.
That these are torsion cosets?
Right.
No, they aren't torsion
Oh.
cosets.
Oh, okay.
The point isn't that. The point is that each of these lives inside this torsion coset.
Okay.
And then the statement for each of these just becomes sort of, if you work through it, it just becomes the statement. Because you're inside this guy is essentially C star to the n minus 1. And so now the statement's reduced down to n minus 1. Okay, so it ends up being a pretty fast way to set it up. So if you set it up this way, well, now what we know, now we're back to the case, well, now we're in the case where V has a bunch of torsion points, so many they can't be captured by sort of any finite set of torsion cosets. So this is good, because now we're able to prove that V is actually all of C star to the n. So that's how we'll finish. Now sort of comes the actual argument. So far we've just made formal reductions. Sort of very carefully made formal reductions to make the actual argument much simpler. So now we're going to pick a sequence. So a sequence like before of Galois orbits of torsion points inside V. Okay? But now we want these guys to be equidistributed. That would be the argument. So we don't want them to stick around inside any torsion coefficient for too long. But because we made this assumption number 3, we can pick the sequence such that for any set chi1 through chi k, C1 through, for any set, I get confused. Such that for any pair chi and zeta, eventually chi of t doesn't equal zeta for any t inside Si. So by eventually I mean for large enough I. For sufficiently big I, any point inside here doesn't lie inside this torsion. Okay? So how do we do it? We'll pick one torsion coset, and then by this theorem of a point not inside there, we'll pick a second torsion coset by this theorem of a point not inside either of these two, and we sort of keep going. Okay, that gives us an infinite sequence, which eventually jumps out of every torsion coset. All right? So these two sort of tricks of making this assumption and taking the sequence are, I don't know how to say it, it's actually quite clever. Like, took a while for the argument to be distilled to this form. They're very simple, but they make the argument very neat. So, how to say it, it's worth forgetting them for a day and trying to recreate them. It's harder than one thinks. Okay. So now we'll make the claim, which is that the measures delta Si converge in the weak star topology to the Haar measure on S1 to the n. Okay? And the proof of this is exactly as before. We have to show for every non-trivial character the sum is 0, so instead we pick some character chi, and we look at the chi of Si's, and then we get roots of unity of larger and larger order, and we show that those equidistribute. Okay? Okay, and so because this is true, so therefore V contains all of S1 to the n, and so V has to equal C star to the n. That finishes the proof. So the statement is certainly true for C star to the n. Okay? Question? All right. So that's our first proof of Lang's theorem. We'll give at least 2 more throughout the course, because the way the subject works is that, Lang's conjecture, Reynolds theorem. The way the subject works is there are sort of progressively more difficult conjectures, each of which has the structure of this conjecture, which we'll talk about, sort of primarily Mann and Mumford and the Andre-Oort conjecture. And the way it works is to prove one of those conjectures, you first come up with a new proof for this one, and then you hope it generalizes. And so this is why there's over 10 proofs of this conjecture now, because it's testing ground for much harder statements. But before we do that, I want to talk a little bit about a generalization of this theorem to something which is sort of more inherently arithmetic. And to do that, I want to talk about the theory of heights, which is also going to be an important tool moving forward. Let me start writing all it down, and then we'll continue next lecture. So what are what are heights? Well, a height is sort of fundamentally, it's some sort of notion of arithmetic complexity. Okay, so we sort of have the notion of size, of sort of the Archimedean absolute value, but that's not always sort of correct for us, because, for example, in the argument we just went through, somehow roots of unity became more and more complicated as the torsion goes to infinity, and that's not captured by the notion of size. So we want to have some way of saying a sequence of numbers, algebraic numbers in particular, becomes more and more complicated. And so the simplest case is if A over B is a rational number, and it's the lowest common denominator, so GCD AB is equal to 1, lowest common form, sorry, yeah. Then we define the height of A over B. B, well, what it means to be complicated, it sort of means either A or B is big, so we can capture that pretty easily just by taking the larger of their absolute values. This is like, we can define this as called absolute height. And then h of A over B, which is just log capital H of A over B, is called logarithmic height. It's the same notion, we take logs, it ends up being much cleaner to work with logarithmic height most of the time. So we'll just work with that. Okay? Okay, so this is sort of a reasonable basic notion of complexity. So we want to do something a little trickier. We want to define height not just for Q, but for Q bar, for all algebraic numbers. So to do that, we'll first reformulate this in sort of a more canonical looking way, so we can generalize much cleaner to other number fields. So recall that Q has sort of many absolute values. So it has the sort of usual Archimedean absolute value. I guess it's called the norm. The Archimedean norm, which like takes number A and it returns what we think of as the usual absolute value of A. And also, for every prime P, we can define the norm, the p-adic norm of A. A here is, I'm going to assume an integer, not equal to 0. We can define the p-adic norm of A to be P to the power of minus n, where P to the n is the exact power of P, which divides A. And so then this extends multiplicatively to the rational numbers, where the p-adic norm of A over B is sort of P to the minus n, where P to the n exactly divides A if n is bigger than or equal to 1. So if P divides A, we sort of take the absolute value of A. P to the m, where P to the m is the exact power of P dividing B if P divides B, and otherwise we just say 1 over here. This is sort of a concrete way to think of it. but it's also just a multiplicative extension of this. So basically, you sort of take out the powers of p from A or from B to make this number relatively prime to p. We call this the p-adic absolute value of A over B. There's a nice notion, it's also a norm. So, in fact, if Q1, Q2 are rational numbers, and this is important, then unlike the usual triangle inequality, with the p-adic norm, you can check you have the stronger inequality, where if you sum the two guys, their size is at most the max of the two guys you're summing. Okay? Okay, so almost out of time. I can probably out of time. Yeah. Okay, let me stop. We'll continue next time.